Okay, so we're moving into day 2 of solving logarithmic functions. This is section 4.5, and we spent a lot of time last time on exponential functions, using logs to undo the exponentials. Now we're going to use exponentials to undo the logs. So when we look at ln of x plus 5 equals 1, we want to think about this x plus 5 being stuck in a log. And the only way to get it out of the log so that we can solve for x is to use the inverse operation, which is called an exponential, with the same base as the log. So what that looks like is we take e, which is the base of the log, and we raise it to this ln of x plus 5. And what that's going to allow us to do is use the exponential here to get rid of the log, to undo the log, and leave us with just the argument of the log left. So it's like squaring a square root. The square gets rid of the square root and it leaves what's left underneath the square root, and this leaves what's left in the log. But if we do that to the left, we have to do that to the right, because if we were solving by squaring, we'd square both sides. Here we're going to use an exponential on both sides. So we end up with just x plus 5, but now it equals e, which is what e to the first is. And so we can then subtract 5 from both sides if we want to know what x is. E is just a number. We take 5 away. And that's our exact answer. We could get an approximate answer if we want to plug it into our calculator. So the same thing is going to happen here. It's just that you can't use this inverse operation until you've isolated the log that you're trying to undo. So since x is stuck inside a log of base 5, this 2 that's being multiplied on has to get divided away before we can use that operation. So divide both sides by 2, and then we'll use the number 5, that's the base of this log, to create an exponential that will leave us with just the argument of the log, which is 3x. But that means on the other side we have the number 25, because we're going to use 5 as a base on that other side as well. And then we just have to divide to figure out what x is. If you have a log on both sides, we had that property that we learned that if you have the log base 3 of this argument is equal to the log base 3 of that argument, we could just set the arguments equal to each other, because the only way the two sides will be equal is if you're doing the same base log on the same thing. And that means subtract x and add 1, and you'll know what value of x will make this true. So number 4, we've got a lot of isolating to do. We're trying to get this log all by itself before we use any exponential. So we're going to subtract 5 and get -1. We're going to divide by 2 and get -1/2. And now that we've isolated our ln, our log, we can use the base of it to create an exponential, e to the ln of x, and then we do the same thing on the other side and allow that exponential and the log to undo each other and leave us with x. And we know then that x is e to the -1/2, which is just a number that I could approximate on my calculator. Number 5, we've got a couple choices here. The square root here that's in the argument means that we're going to have to deal with the fact that x is living under a square root. But we also have a property of logs that says that's not a real big deal, because this 1/2 could just come down in front. So we could really think about this as a 1/2 times the ln of x minus 8, and then we're not dealing with square roots. Then we could multiply both sides by 1/2, and we've isolated our ln without the square root, which makes it a little nicer. And then we can use our base of e to undo and leave us with x minus 8. And then we get e to the 10th on the right-hand side, which again is just a number. So a number that we can add 8 to. And if we want to approximate it, we can. Number 6 has got a star next to it. So stars mean that you might want to think before you jump into how to solve this, because people are tempted to try to go like this. Put a 10 as an exponential here to undo this log, and then a 10 to undo that log. The problem is you've got addition in between them, and you cannot use the exponential across addition like that, just like we couldn't use a log across addition. So what we've got to do first is use a property of logs to turn this into a product. So if we have the sum of two logs, we could think about it as the log of the product of their arguments. And now we can use that base of 10 as an exponential to leave us with 5x times x minus 1, which is the argument, has to equal 100, 10 squared. And now we have a quadratic to solve. So we're going to have to distribute and move the 100 over, because the only way to solve a quadratic is to set it equal to 0. We could divide everything by 5, and then we can factor. Now here's the interesting thing. We get 2 answers, but we need to look back at the original problem and realize that we're not allowed to put negative numbers into logs. Logs have a domain that is greater than 0. So this number that we found here, which is -4, if you tried to put it in and check your answer, what's the log of 5 times -4, your calculator is going to scream at you and say, no, that's a domain error. So this is called an extraneous solution, a solution that comes about because of the strategy we used, but it doesn't actually solve the problem. But the number 5 should solve the problem. So if I say the log of 5 times 5 plus the log of 5 minus 1, I get 2. So the answer 5 is the true answer, and -4 is extraneous. Moving on to number 7. Same thing. We need to get these logs together before we can use our trick of the exponential undoing the log. So pulling together subtraction of logs is a division problem. So I got the log base 4 of this. Now I can use my little trick of 4 raised to all of that, undoing the whole log and leaving me with the argument. 4 raised to the 1/2 on this side is going to be the number 2. So now I can use cross multiplication to solve for x. 2x minus 2 equals x. Subtract 2x from both sides and solve and get x equals 2. If I look at that and try to put it back in my log, I shouldn't have a problem. Positive argument here, positive argument there, but let's just check. So I'm saying that the log base 4 of 2 minus the log base 4 of 1 equals 1/2. Log base 4 of 2 on my calculator is the log of 2 divided by the log of 4, and that's 1/2. The log base 4 of 1 is 0, but you can check it. The log of 1 divided by the log of 4, whoops, I'm not showing you that, is 0. So it checks. Moving on to number 8 here. How do I solve for y in terms of x when I've got logs? So I've got ln of y, I've got 2 ln of x plus ln of x minus 3. So to solve for y in terms of x, what I want to do is pull these 2 logs together again, because I don't want to ever have addition in between my 2 logs when I'm solving. So I'm going to call this the ln of x squared plus the ln of x minus 3. and then I can pull it together to be the ln of x squared times x minus 3. And now I have the log ln of y equals the ln of this function, or this relationship in terms of x. And now if I use my base, e to the ln of y will give me y. And e to this, e to the ln of all this is going to give me x squared times x minus 3. So I've just solved for y in terms of x. Same idea here. I can pull my two logs together. And, oops, nope, don't want to do that yet. I caught myself. The reason I don't want to do that yet is I want to get my arguments the same. So I want to use the same kind of variable before I start pulling things together. This is a y and this is an x. So let's leave the y's on the left and move the x's to the other side. And so now I've got the log base 10, not 4, of y minus 4 equals, the 3 will come up as an exponent. So this will be x cubed. And since it's a subtraction problem, it'll be that x cubed divided by that x. And so the log base 10 of y minus 4 equals the log base 10 of x squared. So now I have, I can do 10 to this power and 10 to that power if I want, or I could think back to this problem here. I've got the same kind of log on each side. I can just set the arguments equal to each other. So y minus 4 equals x squared. So y equals x squared plus 4. I've solved for y in terms of x by getting the logs equal to each other and then setting the arguments equal. This is an application problem for business calculus with logs. If I deposit $500 into an account, that's the principal, and I got the interest rate, and it's compounding continuously. So remember, continuously looks like this. P equals e to the RT. Back up. No, it doesn't. Sorry. The ending balance equals the principal times e to the RT. So sorry about that. Ending balance A equals the principal multiplied by e raised to this power. So the interest rate you have and the time that you're going to keep it invested. But the question here is, how long will it take to double my investment? So the way we're going to use this formula is, we know that we're putting $500 in, that's P, and we want to get $1,000 out, that's double. So I want A to be $1,000 when P is 500. I know that the interest rate is 0.0675, but what I don't know is the time that will make this become $1,000. So this is an equation I need to solve, and that's why it's in this section. So first thing I want to do is isolate my exponential by dividing both sides by 500. So that means that I really didn't need to put in 500 and 1,000. It doesn't matter how much money I have. It will double at in the same amount of time. But in order to figure out what that time is, I need to undo this exponential. So I'm going to take the ln of both sides, and that's going to leave me with the ln of 2, and over here, 0.0675t. I'll divide both sides by 0.0675 to solve for t. And since it's time, I should probably do that in my calculator so I understand what that number really is looking like. It looks like it's going to take over 10 years. So I would say either 10.3 years, or depending, if they only allow me to put it in terms of years, I'll have to say 11 years because it won't have doubled yet in 10 years. To triple, it's the exact same thing, except that I want a 3 on the other side. And that means that it's the ln of 3. And when I ln the other side, I get the 0.0675t. So the only thing that's changing is it's the ln of 3 divided by that number. And so if I go back up to my calculator and I just change that 2 to a 3, it'll take me about 17 years to triple. So there is a formula that you can learn for business that is the ln of whatever you want to do. So if you want to triple, quadruple, take it 5 times, but you put that in the box and you divide it by the interest rate, because that's what we kept doing over and over again. So to quadruple, you'd put the ln of 4 divided by the interest rate. And this little formula comes from what we're doing here with exponentials. Last problem. We've got a function that is a constant times e to a power, and they want me to use this model to estimate what year will the expenses reach $610 billion. So the expenses are given in billions of dollars. So what I really want to know is, when will the left-hand side be 610 if this is the function for the right-hand side? And so I want to solve for t, in other words. So my first step in solving for t is I take the 610 and I divide it by this coefficient so that I've got a number over here that is going to be the way that I'm going to isolate this e. The problem is that as soon as I start to round this, my answer is going to not necessarily match the one that's in WebAssign. So rather than writing that number down like 600, like 2.93 whatever, and not knowing when to stop, I'm going to just keep that as an exact answer, because now I need to take the ln of both sides. So when I ln, if I have rounded this, then my answer is not going to match. So I'm going to keep this as an exact answer when I ln it, and then I'm going to divide by the 0.067, and I'll get my exact time instead of rounding it. So you see, when I first did this division and I saw how messy that number was, then I decided, clear that out. Let's not do that. Let's do the ln of this division problem so that I'm not rounding it. And then when I hit equal to, then I can just divide that by the 0.067 that I want to divide by. And I will find that it's when t is 16, which means if t is 7 matches with 1997, 16 is 9 years later. And so we're talking about 1997 and 9 years later, 2006. So t equals 16 means 2006. So at that point, I will have reached this amount of expenses, $610 billion.